Hey, so we're going to be talking about measurements that are common in Introductory Chemistry, a Chem 101 course, and their associated units. Okay, we're just going to keep this nice and simple. We got four things we'll be talking about today. We'll be talking about length, and we'll be talking about volume. Volume is the third dimension of length. And then we have mass, and then we have temperature. One more thing we'll talk about is we're going to sneak in a discussion relating mass and volume together, and we're going to call that density. All right, so first up, we have length. All right, so length is just a measure of distance going from one point to another. We are in one dimension. All right, common units, just to refresh you, we could be working in the metric system, meters, centimeters, millimeters. We could be working with these sorts of units for longer distances, maybe something like kilometers or miles. Okay, so one thing I'm going to be doing aside between each example is I'm going to be showing how we progress to three dimensions. Right now, we are in one dimension. We're measuring length, and we have 10 centimeters that I drew out here. All right. We're going to go to two dimensions now, and we're going to be talking about area. Okay, area works in planes or sheets, very much like this piece of paper. So we are in two dimensions now. All right, common units, I just wrote the same things except with squares on all of them, like square meters, square feet, things of that nature. Okay, so I had those 10 centimeters from before, right? And now we're going to take it into two dimensions. So we have 10 by 10 here. We don't write 10 centimeters squared. It's 10 times 10, so it's 100 centimeters squared. Okay. All right. Now we're going to move into three dimensions. Okay, so we can have units such as these. I guess if you really wanted to, you could measure stuff in like cubic kilometers or cubic miles, maybe if you're like measuring the amount of gases in the atmosphere. I don't know. Okay, but we're working in three dimensions now. All right, now this is where I can show a nice, cool little prop. Right here I have, ooh, can I fit on the screen? Maybe I'll back this up a little bit. All right, this is a 10 by 10 by 10 cube, okay, block. All right, you can see 1, 2, 3, 10, 10 going that way, and then 10 going along with the height. I'll flip that, show it to you. Okay, there's something special about this block. This block is 1,000 cubic centimeters. All right, write that down. Okay, this is 1,000 cubic centimeters. We got that volume from doing 10 times 10 by 10 to get that 1,000. All right. And what's special about this block is that these 1,000 cubic centimeters, all of this is equal to another unit of volume that we call liters. This is 1 liter. All right. So I'm going to show the significance of 1 liter. You may be used to liters more in the sense of like drinking a beverage. You get a liter bottle or like a 2-liter bottle. And maybe it reminds you, I am a chemist, I'm going to bring out glassware. We would maybe have a container like this for, that looks better, measuring out fluid. Okay. But liter, cubic centimeters, any volume unit will work for any phase of matter, whether it's solid, liquid, or gas. Okay. So back to the liter, though, I want to show an interesting relationship. We just said that a 1,000 cubic centimeters is the same as a liter. All right. Now, the milli prefix means 1,000th of something. So if we have 1 liter, there's going to be 1,000 milliliters in it. Well, both of these quantities, the 1,000 cubic centimeters, the 1,000 milliliters, are equal to 1 liter. We can set them equal to each other, and we'll get a relationship like this. If we were to cancel out the 1,000 on both sides, we would see that 1 cubic centimeter is exactly the same as 1 milliliter. Okay, that's a useful thing to know because sometimes with volumes, you'll see them written one way or the other. It's actually perfectly interchangeable with each other. All right. One thing I do want to know, I'll put it on this post-it note, is if you're going to change out the units, if for some reason you wanted to write a milliliter instead of a cubic centimeter, you would have to just go from there to there. What I mean by that is you cannot write something like that. Milliliters, okay, is already a three-dimensional unit. It's already in 3 dimensions. And so you don't write a cube on it like you do with cubic centimeters. Okay, since centimeters is a one-dimensional unit, you turn it into 3 dimensions with that 3 over there. You don't do that with the milliliter. So this is wrong. Okay, let's just not do that. That would be like the 9th dimension, and I'll leave that for like theoretical physics and mathematicians to figure out. Okay, don't write a 3 over there. Another thing that I've seen people kind of get crossed up with is maybe thinking, how is it that I have a centi prefix here and I have a milli prefix here? Okay, I think the easiest explanation for that is that's just the way the equivalence went. You can clearly see here, going back to this block, I have 1 centimeter here, there, and we go 10 by 10 by 10, and it's 1,000. All right. And it's 1,000 cubic centimeters. And yet, if this is called 1 liter, there should be 1,000 milliliters in it. So it's just, that's just kind of the way it works out, that we happen to have 2 different prefixes here. Okay. Don't mess with them. You can't change this to like an M. You can't change that to a C. That would ruin the equivalency as well. All right. So we'll just stick with this factoid. Okay. Let me pull this up so that you can see this in good detail. 1 cubic centimeter is the same as 1 milliliter. All right, the next unit I want to talk about is mass, okay? And mass is where I have to maybe start getting a little bit more precise or careful with my explanations. I think mass is something that we can relate with. Okay, we think of mass and we think of, oh, that's like stuff, right? And that will turn out to be my favorite definition, but we can maybe get more technical than that. But first, let's introduce some common units. Okay, kilograms, grams, milligrams, micrograms. All right. Those in nutrition fields or maybe some other field, maybe like water quality, maybe they'll see like an MC that is lowercase. Okay. Later on, you're going to see atomic mass units. As you can tell with this power of 10, this is a really dinky number. We use atomic mass units when we're talking about the sizes, or excuse me, the masses of like protons or neutrons. All right. And when we're talking about the masses of like single atoms and isotopes. All right, so, oops, I revealed too much, too late. Oh, whatever, I'll just keep on the video. So I want to show some different definitions of masses, so it's not just in my words, all right? Going to the Merriam-Webster dictionary first, you can read through that. Some things that kind of stick out at me is it pays attention to, or it mentions like the amount of material. Okay, so we associate mass with like how much material there is, how much stuff. If we want to get really technical, it has this word inertia. Okay, it's a property of a body of matter that is a measure of its inertia. So inertia is being taken into account. So just to kind of refresh or define what inertia is the resistance to movement, okay? And so in order to move something, you have to push it or you have to pull it. And in physics terms, we call that a force. Now, this isn't a physics class, so I'm not going to write, hopefully, too many equations. Would I put this equation on one of my Chem 101 exams? I would not, but this is force is equal to mass. Okay, here's that word again, mass, times acceleration. The acceleration is just, you know, how much you're changing the speed of something, okay? So that could be an acceleration you apply, like you're throwing a baseball, or we could just be talking about the acceleration like due to gravity. Then we would find the acceleration due to gravity. You can look it up, but that's around 9.8 meters per second squared on Earth. Here, I'll write that. I know someone wants to write that down since I said it. But that's a force, okay? So basically, we want to be really technical with the definition of a mass. It's the property of matter where the more of this mass property you have, the more difficult it's going to be to push or pull it to move it. In other words, you're going to need more force. So if this mass number goes up, assuming the acceleration number is equal, so is that, okay? So in plain speak, to keep it really simple, the more massive an object is, the harder it is to push or pull it, harder it is to move it. And that is the definition, all right? We can go to the National Institutes of Science and Technology, Standards and Technology. I think it's standards. Oh my gosh, I'm a scientist. I forget what it stands for, whatever. And they get at very similar ideas: inertial property, the amount of matter it contains, or matter, okay? So I invite you to come up with your own definition, all right? My favorite definition, to keep it really simple, it's stuff. All right, so now let's talk density. So density relates mass and volume together. It's the amount of mass that you have in a certain volume. So you can write a density equation like D equals M over V. All right. Just so that people know, others might use a lowercase d, others might use the Greek letter rho. Okay, but I think I'm usually going to be sticking with this, but it's mass over volume. So mass is going to depend on what elements are present in your material. Okay, so you'd have to go to a periodic table to get a general sense of that. I'm not going to be talking about that a ton today, but just to kind of give you a preview for the future. Okay, we can go to a periodic table, and it's going to have something to deal with these bottom numbers. So we go to aluminum, or shall I say aluminium, all right, 26.98, about 27, all right, and then we can go to something like tungsten, 183.84. So if we were going to compare aluminum versus tungsten, we can see that comparing one atom of aluminum to one atom of tungsten, tungsten is going to be a lot more massive. All right, it would be heavier if we were measuring its weight. All right, and I picked those two because I actually have those two elements handy. I have 2 cubic inches of aluminum and tungsten. You can see they're both the same volume, a cubic inch. But let's just listen to the difference in density. Even dented my paper. All right, so you get the idea. All right, so tungsten appears to be, sounds like a more massive element, okay? Um, and But it's not just about the mass of the individual elements. I mean, sure, tungsten is more massive. We saw that in a periodic table as a higher atomic mass number, but it's ultimately about how tightly you pack your stuff into the volume. Even if you have heavy objects, if they're spread out in your sample, then it's not going to be as dense as it could be. So how tightly can we pack a material? Okay. In the chemistry class, that's going to have to deal with the distance between atoms. We don't talk about that too much in a Chem 101 course, maybe a tiny bit later on, as well as packing efficiency, how closely you pack the atoms together. And that can be studied in terms of a material's crystal structure. So without any math, I just wanted to kind of show how density plays out at the atomic level. I'll bring out these little spheres here. All right, so I have 4 of these red spheres. All right, if I arrange them in kind of like a perfect square here, it may look like neat and nicely arranged. Oop, there we go. Um, but I would argue that this is not the most efficient way to pack. In fact, you can see like this large gap here. If I just slide things over, you can see those gaps get way smaller. All right. And so filling the gaps, staggering them is the most efficient way to pack matter. Okay, but that's only one layer. Okay, we live in a three-dimensional world. All right. So I could put maybe the next sphere here. And sometimes nature will do that, but often what nature will prefer is to just, oops, let things slide to the natural middle. Okay, we see that we have a gap for things to sit in. Okay, whereas here there is no gap. So some materials, sometimes you'll see like that direct stacking on top of each other, but often for some other materials, you're just going to pack things as closely as possible. So, but that's going to depend element from element. So that's what I'm talking about in terms of the packing efficiency crystal structure. If that interests you, I'd be happy to make another video or two on that. Just let me know. But that's the idea of density relating mass and volume together. There we go. All right, and then the last measurement I want to talk about for this video, I think we're just doing a quick little overview of a bunch of measurements, is temperature. Okay, so common units for temperature. Okay, I'm in the United States, so weather is often done in Fahrenheit, but for most of the world, it's going to be Celsius. All right. And then we have this Kelvin scale, which people may not be as familiar with. All right. There are mathematical ways to relate these. Okay. I'll write them in case you're curious. You can skip this over if you're like, I'll wait till later. The Fahrenheit temperature is going to be 1.8 times the Celsius temperature plus 32. All right. Some people like to write this in a fractional form. So 1.8 is also known as 9/5, and you can go that way. All right. And then to go between Celsius and Kelvin, you're going to add 273 to the Celsius temperature if you want to be really spot on. You have a high resolution way of collecting temperature data. 0.15 is actually the complete constant. So temperature, some closing thoughts. We associate temperature with thermometers, with the weather, but what does it really mean? Okay. I like to think of temperature as the strength of movement in a material. Okay. So let me maybe bring up some other definitions so you can maybe get around that idea. We'll start with the Merriam-Webster. Okay. They're calling it a degree of hotness or coldness measured on a definite scale. Okay. NIST gets a little bit more specific. How much average energy of motion? Okay, so we're talking about movement, kinetic energy, some things atoms or molecules have. Okay. I like to think of this in my definition. I like to actually I like to use this word strength when I'm talking about temperature, the strength of the motion. Okay. Because what I get scared with is people confusing temperature versus heat, or more accurately, thermal energy. Okay. So let me just write this here as a closing thought. Temperature is not the same thing as thermal energy. Okay. We'll just call that heat in quotations. If you're wondering why it's in quotations, I invite you to go on a Wikipedia rabbit hole or something and check that out. I'll maybe discuss that in another video, but heat. All right. They're not the same thing. All right. They're not the same thing. Temperature, like I said, is the strength of the motions in something. So You have a fire. Fire is very hot. Okay. You're going to have a higher temperature. A common question that's posed is what has more thermal energy? What has more heat? Lighting a match, okay, versus an Olympic swimming pool. Okay. Which one has more heat? Okay. So I'll let you think about that a minute. You can pause this. All right. So the answer is going to be the swimming pool. The swimming pool has more heat. It has it's way bigger. It has overall more vibrational energy. But if we're talking about the strength of the vibrations, they're not as strong as what's happening in the match tip. The match tip, you have your atoms moving way faster, stronger thermal energy compared to the lower temperature of the swimming pool. Okay. So hopefully that helps elucidate the difference between those two. All right, those are the four main measurements we'll do in the Chem 101 course. If there's a little other ones later on, we'll talk about those, but those are going to be the sort of measurements and therefore the sort of units you're going to be seeing very often in this course. All right, hope that helps. Thanks and take care.